Good morning, dear student. Today we discussed the next important point of photochemical reaction, that is quantum yield. So this quantum yield, it is also known as quantum efficiency. So the photochemical reaction is of two types. One is primary process and another is secondary process. So first, the photochemical reaction is of two types. First, that is primary process, and second, that is secondary process. So this photochemical reaction or photochemical process, which have two types, one is primary process and another is secondary process. So what is this primary process, what is this secondary process? We are discuss this primary and secondary process for study of quantum yield. So the second law of photochemical reaction or photochemistry, that is Stark-Einstein law, it gives the idea about one molecule, if it is present, it will absorb one quanta of radiation. So we know that the statement which is given by Stark-Einstein law, that is, if one molecule is present, it will absorb one quanta of radiation. And for this process or for this reaction, that is, one molecule absorb one quanta of radiation, get activated and convert into the product. So for this reaction, or this reaction is considered as a primary process. This reaction is considered as a primary process, and for this reaction the quantum yield is equal to unity. The quantum yield is equal to unity. So for primary process, so the first point is the primary process, the quantum yield it is denoted by symbol phi is equal to 1, that is unity. Quantum yield, it is denoted by symbol phi. Okay, it is denoted by symbol phi. So for primary process, the value of quantum yield is equal to unity. So what is primary process? One of the molecule absorb light radiation, goes into the higher energy state, that is excited state, and then convert into the product. But in practically, this is a very limited process, or we can say that the primary process, not only primary process in photochemical reaction, but there is a secondary process also there. So this quantum yield, that is the quantum yield is unity for primary process. It is only applicable, that is quantum yield is equal to 1 or unity, it is only applicable for primary process. It is not applicable for secondary process, that is important. So the phi which is equal to 1, it is only applicable for primary process, it is not applicable to secondary process. The primary processes are very limited, and therefore we will discuss the secondary process, and for the secondary process the value is not equal to unity. That is very important. For secondary process, the value is not equal to unity. So this value, that is the quantum yield value or the phi value, it will deviate from the unity for the secondary process. It will shows large deviation from the unity for secondary process. So it will lie, it ranges from 0 to 10 raised to 5 to 10 raised to 6 unit. 10 raised to 5 to 10 raised to 6 units. So before discussing the quantum yield, what is the formula for quantum yield and what are the causes, we will discuss these phenomenon such as primary process, secondary process. So according to the Stark-Einstein law, when molecule absorb light radiation, goes into the excited state and convert into the product, this process is considered as, or this reaction is considered as primary process. For primary process, the quantum yield is equal to unity, but for secondary process the quantum yield is not equal to unity, and it ranges from 0 to 10 raised to 5 to 10 raised to 6 unit. So it will shows large deviation, it will shows large deviation from unity as the process changes from primary to secondary process. So this is the important point regarding to the quantum yield. So what is this quantum yield? Quantum yield is nothing but quantum yield, it is also known as quantum efficiency, and it is denoted by symbol phi. So quantum yield is the ratio of number of product molecule form, number of product molecule form to the number of quanta absorbed, number of quanta absorbed. So it is the ratio of, so quantum yield or quantum efficiency, it is the ratio of number of product molecule form to the number of quanta absorbed by the molecules, number of quanta absorbed by the molecule. In other words, we can write, in other words we can write phi, which is equal to number of reactant molecule consumed, number of reactant molecule consumed divided by the number of quanta absorbed. So number of product molecule form or number of reactant molecule consumed divided by the number of quanta absorbed, or we can write phi or quantum yield is equal to, so the rate of reaction, a rate of reaction divided by the number of quanta absorbed, light radiation absorbed. So it is the ratio of the rate of reaction divided by the number of quanta absorbed. In terms of molar quantity, if you express this term, that is quantum yield, in terms of molar quantities, then we can write phi which is equal to, for molar quantities. So this is for molar quantities. So phi which is equal to number of moles of reactant, number of moles of reactant react in given time to the number of Einstein absorbed, in same time, So in case of molar quantities, number of moles of reactant react in given time to the number of Einstein absorbed in same time. So one Einstein, if you consider the molar quantities, one Einstein is equal to 1 mole of photon, 1 mole of photon or 1 mole of quanta. So for molar quantities, quantum yield is equal to number of moles of reactant react in given time to the number of Einstein absorbed in the same time. So this is regarding to the quantum yield. So the quantum yield is equal to unity for primary process, and it follows the second law of photochemistry, that is the Stark-Einstein law. For primary process the value is unity, but for secondary process the value is not unity and it will varies, it will shows a large deviation from 0 to 10 raised to 5 to 10 raised to 6. Then we will discuss what is quantum yield. It is the ratio of the rate of reaction divided by the number of quanta absorbed. In case of molar quantities, the number of moles of reactant or the number of moles of product. So in this case the number of moles of reactant react or number of moles of product form to the number of Einstein absorb by number of Einstein absorb in this given time. So this is regarding to the quantum yield. Let us see the next point. It is also important, the causes of low quantum yield and high quantum yield. So let us see the first point, that is the causes for low quantum yield. Low quantum yield. The causes for low quantum yield. So let us see. So why we get a low quantum yield for particular reaction. So the first cause for this low quantum yield is that activated molecule. So we know that a molecule absorb light radiation, goes into the higher energy state and get activated. So this activated molecule gives its energy to another molecule which is inert or it is non-reactive. So the main cause, the first cause for low quantum yield is that the activated molecule does not convert into product, it will transfer its energy to another molecule which is non-reactive. So this is one of the causes, this is one of the cause for low quantum yield, that is activated molecule transfer the energy, activated molecule transfer the energy to inert molecule, activated molecule transfer the energy to inert molecules. So this is first cause. Second, the process of deactivation. We already discussed the process of deactivation. It is also responsible for the low quantum yield. That is, we discussed, that is a radiative process. A radiative process such as fluorescence. First, that is fluorescence, and second, that is phosphorescence. So this radiative process we discuss in Jablonski diagram. What is fluorescence? Activated molecule goes into the higher energy state, and when it return to the ground state, it emits certain radiation, and this radiation is considered as, the emission of radiation is considered as fluorescence. It is occur from excited singlet to the ground state, while this is also the emission of radiation, but it is also known as the delayed fluorescence. It will emit radiation from excited triplet to the ground state. So these are the radiative process. So in this case, the reactant, the activated molecule, is not converted into the product. In this radiative process, the activated molecule is not converted into the product, and they will return to the ground state with emission of radiation, and therefore these processes are also the causes. These processes also cause the low quantum yield. So it is also responsible for the low quantum yield. Another important process, that is non-radiative process. Non-radiative process we will discuss in Jablonski diagram, that is internal conversion and intersystem crossing. The processes, that is first internal conversion and second, that is intersystem crossing. So these are two non-radiative processes which also results for low quantum yield. So this non-radiative process we discussed, that is internal conversion, that is the transformation of molecules from excited singlet state, that is excited singlet third to excited singlet second, it is considered as internal conversion. While this intersystem crossing, that is the transformation from excited singlet state to the excited triplet state. So this transformation, they are non-radiative transformation, no emission of radiation, but in these processes the activated molecule return to the ground state, but it is not converted into the product, and therefore it will results into low quantum yield. So these are the three important points, that is activated molecule transfer its energy to the inert molecule, second a radiative process, and third non-radiative process are responsible for low quantum yield. So let us see some example of this low quantum yield. Examples for this low quantum yield. So first example, that is the reaction between H2 plus Br2 in presence of light radiation to gives twice HBr, its quantum yield phi, which is equal to 0.01. Another example for this low quantum yield is that is the reaction of, if you consider the reaction of decomposition of ammonia in presence of light. So where we get N2 plus thrice H2, its quantum yield is equal to 0.1. And another example, that is, if you consider another example, that is twice Hi, so it will gives I2 plus H2. So for this reaction, quantum yield is equal to unity. So these are the examples of low quantum yield. So three causes: first, it will transfer energy to the another molecule which is non reactive; second, radiative process; and third, non radiative process. In these processes, the molecule is not converted into the product, and therefore the quantum yield is very low. So these are the example, that is reaction of H2 plus Br2, then decomposition of ammonia, then Hi in presence of light. So it will gives the product, but the efficiency, the quantum yield is very low for this reaction. So let us see the second point, that is causes for high quantum yield. Second, that is causes for high quantum yield. High quantum yield, causes of high quantum yield. The first point which is responsible for high quantum yield is the chain reaction. So we already discussed chain reaction in physical chemistry. So the molecule which absorb light radiation goes into the higher energy state, get activated, and this activated molecule react with another reactant molecule, and a chain reaction is continue. So it will react with another molecule, forms another activated molecule, then it again react with another molecule. So the continuation, that is the step of propagation, is continue, and which results into high quantum yield. So main cause for high quantum yield is chain reaction. It is very important, that is chain reaction. Another point is that it will transfer the energy to the another molecule, transfer energy to the other molecule, transfer energy to the other molecule. So the first cause is chain reaction, second transfer energy to the other molecules. So it undergo secondary process. So a molecule absorb light radiation, goes into the higher energy state and transfer its energy to the other molecule. So by transferring the energy to the other molecules get also get activated and converted into the product. And this is the cause for high quantum yield, that is chain reaction, transfer energy to the other molecule. And third important point, that is the disintegration of the molecule. Disintegration of the molecule. Disintegration of the molecule. So if a single molecule is present, it will absorb one quanta of radiation, goes into the higher energy state, but by the absorption of light radiation, it will disintegrate and forms two molecules. So these two molecules again absorb a radiation, light radiation, goes into the higher energy state and convert into the products. So these are the causes for the high quantum yield, that is the molecule undergo chain reaction, molecule undergo secondary process, so transfer its energy to the other molecule, and third, that is disintegration of the molecules. So if we consider the example of this high quantum yield, that is example, if you consider the example is, that is H2 plus Cl2 gives twice HCl. It is an example of high quantum yield, that is phi, which is equal to 10 raised to 5. Another example is that CO plus Cl2 gives COCl2. Again, the phi is equal to 10 raised to 6. So this is regarding to the causes of low quantum yield and high quantum yield. So primary process, for primary process the quantum yield is unity, but for secondary process the quantum yield is not equal to unity. And what are the causes? The causes for low quantum yield is what? It will transfer energy to the other molecule which is not reactive. Then the radiative process, non-radiative process are responsible for low quantum yield, while for high quantum yield the chain reaction is the important factor which increases the quantum yield. Again, the secondary process, transfer of energy to the other molecule, and the disintegration of the molecule. And these are the examples of the high quantum yield. So this regarding to the quantum yield. So quantum yield, it is the ratio of number of product molecule formed divided by the number of quanta absorbed, or number of moles of reactant react, or number of moles of product formed to the number of Einstein absorbed. So this is all about the quantum yield. In next lecture we will discuss the photochemical reaction, that is the prompt reaction and delayed reaction. So what is the difference between prompt reaction and delayed reaction? Thank you.